Assalamu alaikum and welcome to this video. In this lesson, we'll learn about the frequency distributions, which is a very simple and easy to understand concept because it's just a table or a graph that records the frequency or count of occurrences of a value or range of values in a data set. And we are going to see examples of it in a while. For discrete or categorical data, frequencies are recorded for each unique category or label, such as in this case. So if we have the grades of students recorded in a data set, we can pick the unique categories or labels in this case, which are A, B, C, D, F. So for this, the data would have been a collection of values A, B, C, however many. And here we have recorded the frequencies. So this means that the data set contained 5 A's. There were 12 B's, C were repeated 9 times, then 4 D's and 1 F also. And when we add all of these values together, it is going to give us the total size of the data set. This is the counts or the frequency of each class or each category here, in this case of the categorical data. But for continuous data, we cannot do this. The reason is that we cannot possibly list all of the unique values which are possible on a continuous scale because those are going to be infinitely many. So what we do is we divide the entire range of the data set into subranges and we call them classes or intervals. And then we record the frequencies or counts of values occurring in each of those intervals, such as in this case. So instead of recording the grades, if we record the scores of the students against those grades, such as A, अगर अब ये hypothetical distribution है of marks. So if A is ranges from 90 to 100 marks. This is one sub-range or one class interval. And 5 means that there were 5 values which occurred in this range. Now, this means those could be any values. वो 91 भी हो सकता था, 99 भी हो सकता है, 100 itself can भी हो सकता है. Yeah, any value between 90 and 100 inclusive will be counted as belonging to this interval. Similarly, 80 से 89 में जो values है वो यहाँ आएंगी, 70 से लेके 79 तक यहाँ आएंगी, and so on. So this is for the continuous data और ये discrete data के case में है. Now let's have a look at some examples. First, for the discrete data, in this case, we just have to count the number of values for each of the category. So this is an example here. If there are 20 students who came for admission to a UG program and there were 3 options from which they could choose for their majors, which could be CS for the computer science, SC for software engineering, or DS for data science. और अगर उनके रिस्पॉन्सेज ये थे, ये 20 रिस्पॉन्सेज हैं जो हर एक स्टूडेंट से पूछा गया और उन्होंने ये कहा. So we can make the frequency distribution table for this very conveniently. Let's draw the frequency distribution table and fill it up. And we can use a tally. If we are doing manual work, we can make a tally. First, I'm going to draw the table and then use the tally to count. Here, I'm going to list the categories. And luckily, we have just 3 categories, CS, then DS, and then SE. Here, I'm going to make the tally. And from that, I'll record the frequency. So how we use the tally is it's just to make our work easy and so that we do not miss any entry. I'm going to count 1 entry for the corresponding category and put 1 bar here. Next entry और एक और bar इधर आ जाएगी. Then these are not CS. Then another CS here. I put 1 bar. और ये काम करते हुए हम बहुत मुश्किल होगा कि कोई वैल्यू आप मिस कर जाए. So but when it's the 5th entry, we're going to put a diagonal over this to make 1 block. And now we know that 1 block means 5 entries. Next, we'll start the next block, this one. So we put 1 for the next block, then another one, another bar, and finally the last CS and another. And now from here we can see that there are one block which is 5 plus 3 which is 8. So there are the count for CS is 8. We can do the same for DS1. It's 1 bar here. Then second DS, and why we cross it in the data set is so that we do not miss an entry. And at the end, we'll make sure that all of the entries have been crossed out. And also it doesn't interfere with the counting of the other next categories. It's the fifth one and then the last one, and we get 1. And similarly, when we do for SC, it's going to be 1, 2, 3, 4, 5, 6. So I'll just do it this way quickly. And we get this 6 and 6. So the total count is 20 and we get this. This is how you make the frequency distribution table, which you have seen that it's very easy. And this is it. So the total count is 20, which is the count of the data set. Now, let's see another example. It says that there were 90 people who entered a shopping mall and they were asked to pick their favorite food from 4 options, including biryani, burger, korma, and pasta. 50 of them chose biryani, 10 burger, 1 favorite korma, and the rest voted for pasta. And so the counts are now given. So we do not need to make tally. The counts are already given. This is the frequency distribution table for it. 50 for biryani, 1 for korma, 10 for burger, and the remaining were 29 for pasta. The total sum is 90. And here is the relative frequency. How we calculate relative frequency is the frequency of this category or class divided by the total frequency gives us the relative frequency of this class. And we do it for all of those classes. When we add up all of those relative frequencies, they must sum up to 1 because that's the whole. Okay, now let's see how we can construct the distribution tables for the continuous data. अच्छा, जैसे हमने पहले बात कर ली है, in case of continuous data, the data will be split into ranges of values. The entire range will be actually split into subranges, and we'll call them classes or intervals, such as 10 to 20, 21 to 30, 31 to 40, and so on, depending upon the range of your data set. There are some important considerations for the classes or intervals. The class limits, which are also known as the endpoints, class widths or class sizes, and the class boundaries. And now we're going to see what each of these means. Class limits are the highest and lower values included in one class or one interval, which is basically a subrange of your data. Class limits of 2 classes cannot overlap. This is because one data element cannot belong to 2 different classes. For example, in case of the grades or score examples, for to be more precise, the value 89 would belong to just one class interval. It cannot belong to 2 different class intervals. So for this reason, the class limits must not overlap. For example, in the interval 10 to 20, 10 is the lower limit, while 20 is the upper limit. They're also known as endpoints of an interval, and generally the classes are listed either in increasing or decreasing order. Now, class width is the range of values, including the limits that belong to this class. They're also known as class size. Class width is calculated by this expression, which is upper limit minus the lower limit plus 1. And 1 here is basically the smallest unit of measurement. So we're assuming that for routine data sets, it's just the smallest unit is 1, such as in our score example also, it's 1. If you're not scoring the points as fractional values, the least possible score is going to be 1. So for this reason, we add this. But if it's a different unit, if the smallest unit of measurement is different, then it is going to be that. Such as if your data is length record Kivian and your data is recorded to 1 decimal place precision, such as 5.3, 2.1. So in this case, the smallest unit that can be measured is 0.1. So that will be added instead of 1 in such cases. But usually it is 1. A class width for the interval, this is an example. If we have the same example interval 10 to 20, the class width is going to be upper limit, which is 20, minus the lower limit, which is 10 plus 1. Again, since assuming that this is the smallest possible measurement, it's going to be 11. The upper limit of a class. Now, this is an important point. If we are given that the upper limit or the lower limit of a class is 21 and the width of class is 5, the upper limit is going to be 25 and not 26, which is the first thing that comes to mind. The first thing and the easiest one is to just simply add 5 to 21 and get 26. But this is not the case because the upper limit is calculated by rearranging this expression. So if I take the upper limit out from this expression, it is going to be upper limit. I'm going to write it upper for short. Is going to be class width. I just rearrange this equation. Class width plus lower bound value, the lower limit minus 1. So in our case, the class width is 5 plus the lower value is 21 minus 1. It is going to be 25 and not 26. So this is how you're going to work either class widths or the upper or lower boundaries, lower limits, because there's a concept of boundary also. And here is what it is. Class boundaries are basically the borders of classes which are extended beyond the endpoints of the class so that two adjacent classes on either side, they overlap, their boundaries coincide, they touch each other. And this is so that you eliminate the gaps for the visual representation, graphical representation that we are going to see in a while. उनको बनाने के लिए we do not want gaps between the intervals. So for this reason, the intervals are extended beyond the endpoints to mark the boundaries which coincide between adjacent classes. और वो किस तरह होगा? For two intervals such as 10 to 20 or 21 to 30 का अगर दो intervals हैं, the boundaries are going to be for the first interval 9.5 and 20.5. How? It's extended a little to the left for the lower endpoint and to the right for the upper endpoint for both of those classes. So this is the boundary for the this class, which is 10 to 20. And for the next class, which is from 21 to 30, it is 20.5, which coincides with the upper boundary of the previous class. Now, the upper boundary for the previous class and the lower boundary for the next class, they coincide. And the upper boundary for this next class is going to be 30.5. So it is like we had this interval, if I mark it this way, from 10 till 20, it was this. And then from 20 to 21. 21, sorry, to 30. We have this. Now, the boundaries are extended beyond this. So for this, it's going to be extended to the right. But for this lower boundary of the next class, it's going to be extended to the left. So this boundary for both of these adjacent classes, they overlap here. And had there been a class interval before this, the boundaries between these two endpoints would have coincided. So this is what the boundaries represent. And they are for the histograms, which actually we're going to see in a while. The extension is half of the smallest unit of measure. So now the question is how much to extend to the left or right. It is equal on both sides, but how much is it? It's actually the half of the smallest unit of measurement. So up till now, we've seen cases where we used 1 as the smallest unit of measurement. Just a score के example में भी ऐसे किया था. लेकिन we also saw an example of heights के लिए अगर हम करते हैं ना तो 5.2, 5.3, 6.1, 4.8. अब इसमें आपकी precision जो है it's 1 decimal point. So the smallest measurement that can be made in this data set is 0.1. So in that case, if it is 0.1, the extension is going to be half of this 0.1, which is 0.05. So for example, if the interval is 1.5 till 2.5, let's calculate the class width first. Here we are going to have 2.5, which is the upper limit, minus 1.5, which is the lower limit, plus 0.1, which is the smallest measurement unit. So here it is 0.1 and not 1. And this is going to be 1.1. And the class boundaries are 1.45,
we subtract 0.05 from the lower limit and add 0.05 to the upper limit. So we have 1.45 till 2.55, the class boundaries. And the next class interval would be, how do we calculate the next class interval? If it is a contiguous representation of this, it's going to be, and there are no gaps, it's going to be 1.5 till 2.5, which is the first class interval, and the next class interval. Now I'm writing the endpoints, not the boundaries at this moment. So the next class, how you're going to calculate, it's simply that you add the class width to the first to the lower limit, and it is going to be 1.1 added to 1.5. It's going to be 2.6, and this coincide this corresponds with this also. The next value is going to be 2.6, and similarly, I'm going to add 1.1 to this to get 3.6. So the next interval is going to be 3.7 till 4.7. Here we are going to have 5.8, 6.8, and so on. And for the boundaries, it's the boundary for this is going to be 2.55. Here it is going to be 3.65. Here it is going to be 4.75 and 6.85 and so on. And the lower side, it is going to be 1.45. Here it is going to be 2.55 because it's going to be the same value. So whatever you write here can come here. The upper boundary of the last class is going to become the lower boundary of the next class. Okay, so let's see an example. These are the scores of students in midterm exams, and 50 of them. And let's consider this data for a while. And we find out that the smallest value is 1 here. And we also see the precision, the scale of this data is the smallest unit of measurement is also 1. And the highest value represented is 90. And there are many different values between this range. Now, in order to make the frequency distribution table, we first need to decide about the number of classes. This is important. Either you should be knowing the width of the class, or you should be knowing the number of the classes to begin with. So if someone tells us that the number of classes is 5, we now need to find out the width of the class or the class size, which is done using this expression, which is the range of the data divided by the number of classes. Here we have, okay, we made a mistake here. It's not 90. The highest value is actually 98 here. Yes, it's 98. So it's 98. 98 minus 1 divided by 5, the number of classes, and this gives us 9.4. Of course, the the width, in our case, since we do not have this 0.4 or decimal precision to this point, and the smallest measurement is 1, we're not going to accept this. In this case, it's going to be rounded up to the next integer. In any case, even if it is some value lesser than 0.5 in on the decimal place, it's still going to be rounded up to the next integer because our smallest unit of measurement here is 1. So 20 is going to be rounded up to 20. The class width becomes 20. And now we need to find out the class intervals and boundaries. Let's start this, beginning with the lowest value that we have 1. Now the width of the class is 20. And the upper limit, how do we calculate the upper limit? We know the expression. Upper limit is equal to the class width plus the upper plus the lower boundary limit minus 1. So in our case, it is 1, which is the lower boundary, plus class width, which is 20, minus 1. So it's going to be 1 till 20. The next one is going to be 20. And now we just need to keep on adding the width to each of them. Here we add 20 to get 21, then we add 20 to get 40, then it's 41 till 60. Here it's going to be 61 till 80 and 81 till 100. And that's it. We do not need to go beyond. The reason is that we do not have data beyond this. And then we need to record the frequencies. And now you can again make tally to do this so that you can do it easily and you don't miss out on values. And for that, for example, if we have, starting from the first point, we have 26, we are going to find out which range it belongs to. इस interval में आएगा तो मैं यहाँ पर एक बार लगा दूंगी. Next one is 46. I crossed that out. मैंने गलत कर दिया. 46 कहाँ आ रहा है? इस interval में. I'm going to mark 1 here. Then 87, 87 जिस interval में आ रहा है, आप वहाँ पे बार लगा देंगे. Similarly, 74, इस interval में आ रहा है, इधर आ जाएगा, and so on. So we are going to keep on doing this and make the table. And then based on the tally, we are going to count the frequency. But here we already have this table, and this is it. The class intervals, the same way as we have calculated the tallies and their frequencies. Now, the class boundary, since we have 1 as the smallest unit, we're going to subtract 0.5 from each of the lower limit and add 0.5 to each of the upper limit. So it's going to be 0.05 and 20.5. And after that, you just need to do it for the first class. When we calculate the class boundary for the first class, after that, you just need to keep on adding the class width. Keep on adding the class width to each next value, and you get your boundaries. 0.5, 20.5, 40.5, 60.5, 80.5. Similarly, the upper boundary of the first class, 20.5, now keep on adding 20 to each. 40.5, 60.5, 80.5, 100.5. That's it. It makes it easier. Okay, now how we can visualize this data. For the discrete data, we can have count plots, which are bar charts with bars representing the counts, as simple as this. We've been working with these all our lives. We can see at a glance that highest frequencies for CS. After that is DS and SE, they are same. Then for the continuous data, we have histograms, which are, this is the same example that we constructed in the previous slide. And now here you see the intervals at the bottom. Because now we do not have categories, rather it's intervals. And usually for histograms, the x-axis is marked with the class boundaries instead of intervals, because in intervals there's gap. In case of the boundaries, so you do not see a gap. It's just for the sake of labeling that we have the intervals. Actually, why these bars, they're coinciding with each other, is that they've been plotted on the class boundaries rather than on these. क्योंकि अगर इनके ऊपर किया जाता तो 20 के बाद 21, 20 और 21 के दरमियान में फिर गैप आता. लेकिन यहाँ पे ये बार्स को इंसाइड क्यों कर रही हैं? बिकॉज दे हैव बीन प्लॉटेड ऑन दी बाउंड्रीज. तो जो हिस्टोग्राम्स है, दे आर प्लॉटेड यूजिंग द क्लास बाउंड्रीज. और यही हमने देखा था कि हमें बाउंड्रीज क्यों चाहिए, सो देयर आर नो गैप्स. We have the same example, and this was the frequency. Cumulative frequency is the frequency of this class plus all the classes above it. And in this case, we'll call it below it because these are smaller values. So this class interval, there is nothing before this, so we have just 10. But this interval, it has one class before it, and we add 10 to 8 to get the cumulative frequency of this class, 18. Basically, the idea of cumulative frequency says that if someone asks about what the cumulative frequency of this interval 21 till 40 represent, it says how many values are there in the data set which is less than or equal to 40. So for that, you're going to add the frequency of this class plus the frequency of all the classes before it. So in this case, it's going to be 10 plus 8, 18. Then for the next one, it's going to be 18 plus 11, 29. Then 9 plus 9, 29, 38, and so on. And the cumulative frequency of the last interval should be equal to the total count of the data set. And this is the histogram for the cumulative frequency. You can see the increasing trend because the cumulative frequency bar chart or histogram is always going to be an increasing trend. Okay, now for the same example, we're going to calculate the relative frequency, and here this the frequency, and now we calculate the relative frequencies by just dividing the frequency of the class by the total frequency or the total count. It's going to be 0.2 for this, 0.16 and all, and we know that these relative frequencies should sum up to 1. And then when we plot it here, it has a similar shape as the frequency histogram. And this one is when we plot the relative frequencies, it's actually equivalent to the probability distributions, which we are going to see now. With very small bin width, a bin is basically the in-class interval. And if we keep on reducing the size of the class interval or the bins, the relative frequency histogram can be approximated by a curve called probability distribution plot like this. So you see the class intervals, when they become very small, we can have this very fine plot, this over them, and you see this very small space which will not be covered by this plot on both sides. But this can be a very good approximation of that. So this distribution plot gives a very quick idea of the central location from here, such as in this case, you can identify that the central location is 64. Here we can identify that the data is skewed to the right. It has a longer right tail. How much variation the data has from here, you can see that the values, they range from somewhere 60 to here 67 or so. And we can also see that there are fewer values from 66 onward and 62 backwards, and there are more values in this range and so on. So we can have an idea of variability and the skewness as we discussed. So we can see that this graph is skewed, but this one is not. So we are going to see many of these probability plots and very frequently in our course. Um, More on the distribution plots, many different probability distributions exist which are known, and these are some of them, and we are going to see a few of them in due time. We'll study binomial, uh, Poisson, geometric, and the normal distribution, which is very popular. The most popular is the normal distribution or the bell-shaped plot, which is this one, which is also known as the symmetric distribution. The distribution plots give a visual summary of the data as we've seen. So this one is symmetric or normal. This one is skewed to the right. It has a right tail which is longer. This one is skewed to the left. It has a left tail which is longer. And this is the distribution of mean, median, and mode. In case of left skew, we have mean smaller than median, which is smaller than mode. In case of right skew, we have mode, which is the smallest value in terms of magnitude because it's towards the left. Median is greater than mode, the value, and mean is greater than median. We can discuss some more about the plots here. Left skew distribution has a longer left tail. It's also known as negatively skewed distribution, as in this case. So इसकी जो left tail है ना वो लंबी है. अब इसका मतलब क्या है? Mod, of course, is going to be the highest peak, as we've discussed. Mod is going to be a point which is the highest point on your plot because this basically represents the frequency or relative frequency to be more precise. And this one, this point is the mod. Now, on the x-axis, this is the range of values. And tail towards the left indicates that there are a few, because you see the height here in this range is very small. It's not very high. The plot is very touching the x-axis here, which means that the frequency of the values here is very low. And these are basically few outliers, which are very different from the other data. So these are quite extreme outliers on the left, which are very small values. And we can also see that the plot has a higher height in this area, which represents the values of higher magnitude. So this indicates that this data set represented by this distribution plot has values of more values of higher magnitude यानी कि बड़ी जो वैल्यूज है ना वो ज्यादा है। तो अगर सपोज ये रेंज यहाँ पर 10 था और यहाँ पे 90 है, तो इसका मतलब है कि ज्यादा वैल्यूज हैं जो कि हायर 90 की तरफ हैं। ठीक है, यानी कि इस रेंज के अंदर ज्यादा वैल्यूज है। इफ सपोज हियर इट्स 50, so there are more values which are greater than 50 than which are smaller than 50. But why is the mean towards the left? Is because there are few very extreme outliers which are very small values which actually pull the mean towards the left. Okay, this is what we can interpret from a left skewed distribution. And the mid value is greater than mean, which is obvious here. Right skewed distribution has all of the opposite things. Here the mean has highest magnitude, and it is because the very few extreme values with very high magnitude, they pull the mean towards the right. And here again, the height of the plot is it's not that high here, which means that the frequency of these values is very small. So these are rare values, and they're also very extreme. That is why we have the plot skews very much to the left. The mid value is smaller than the mean. Here, median is to the left, so the magnitude of mean is smaller. Of median is smaller than mean in case of right skew, which is also known as positive skew. And the we've talked about the outliers, and this also tells us that this area has higher frequency, which means values of lower magnitude have higher frequency as the values as compared to the values of higher magnitude. यानी कि इस डेटा सेट के अंदर lower magnitude की values ज्यादा है. And here is the empirical rule which we are going to be using very frequently. What it says is, these are some symbols that we are familiar with, but we can recall. This is mu, which is the mean. This is sigma. This symbol is the standard deviation. And here, this is a symmetric distribution, and the mean is in the center. And from this point to this point is one standard deviation below the mean value. And from this point to this point, it is mu plus 1 sigma, which means one standard deviation above the mean value. We add the standard deviation to the mean to get this to this point, and then mu plus 2 sigma, we add two standard deviations to mean, and plus 3 sigma, and so on. And on the left side also, we subtract 1, 2, and 3 sigmas. And it says that in a symmetrically distributed data set, 68% of the values, यानी पूरे data set का जो 68% है, it's going to fall between the range. The range of the values is going to be from mu, mean minus 1 sigma, to mean plus 1 sigma. So for example, if the mean of a data set is 15 and 3 is the standard deviation, तो इसका मतलब ये हुआ कि 68% वैल्यूज आपके डेटा सेट में, और अज्यूमिंग कि अगर हमारे पास 100 वैल्यूज हैं डेटा सेट में, तो इसका मतलब ये हुआ कि 68 उनमें से, उन 100 में से 68 वैल्यूज 15 minus 3 which is 12 से 15 plus 3 which is 18, यानी कि 12 से 18 तक के दरमियान की वैल्यूज होंगी. ठीक है, इसमें जो 12 से लेके 18 तक की जो वैल्यूज हैं वो 68 वैल्यूज होंगी, which in case of 100%, 100 data है ना, तो 68% का मतलब है कि 68 of those values. Similarly, the next this bar says that अगर हम इसको extend कर दें 1 sigma प्लस एंड माइनस 1 सिग्मा के बजाय म्यू माइनस 2 सिग्मा एंड म्यू प्लस 2 सिग्मा के दरमियान में अगर देखें, तो 95% ऑफ द डेटा विल लाई इन दिस रेंज. और बढ़ा दें तो 99.7% of the data is going to lie between within the three standard deviations, which means mu minus 3 sigma से लेके mu plus 3 sigma तक 99.7% data आ जाता है, which leaves only 0.3% data outside this range. यानी कि इसका आसान अल्फाज में, सादा अल्फाज में इसका मतलब ये है कि अगर किसी डेटा सेट की डिस्ट्रीब्यूशन नॉर्मल है, वो सिमेट्रिकली डिस्ट्रीब्यूटेड है, तो उस डेटा सेट के अंदर बहुत कम ऐसी वैल्यूज होंगी जो कि म्यू के 3 सिग्मा से आउटसाइड हो, ऑन आइदर साइड. So this is what the empirical rule states.